What if reality itself is a never-ending pattern? Welcome to the astonishing world of fractal geometry, where every curve, coastline, and cloud hides a secret of infinite complexity. In the next few minutes, we'll zip through 10 mind-blowing facts that will make you see the world in a totally new way. First up, imagine standing on a beach, measuring the shoreline. The more you zoom in, the longer it gets, because coastlines are fractal, never truly ending no matter how precise your ruler. That's why scientists still debate the true length of our planet's borders. Now, look at a simple fern leaf. Its delicate fronds split into smaller copies of themselves, a perfect natural blueprint of recursion. Even the crazy broccoli called Romanesco follows the same rule, each tiny bud echoing the whole. This pattern isn't a coincidence. Evolution seems to love fractal designs for efficient growth. Let's dive into mathematics. The Mandelbrot set, an iconic black and white swirl, holds infinite detail inside its boundary. Zoom a million times and you'll find entirely new, self-similar islands that were never there before you looked. It's a visual proof that infinity can live on a flat screen. But fractals aren't limited to pretty pictures. In the chaotic world of finance, stock prices bounce up and down in ways that mirror fractal dynamics. The same equations that describe a tiny daily swing can also model a massive market crash, hinting at a hidden order beneath the apparent randomness. Our brains, too, dance to a fractal rhythm. EEG recordings reveal that neural firing patterns repeat across scales, from slow waves to rapid spikes. Some researchers argue that this scaling law might be the key to understanding consciousness itself. Look up at the night sky. Spiral galaxies, with their sweeping arms of stars, are cosmic fractals. Each arm contains smaller clusters that echo the galaxy's overall shape, a celestial example of self-similarity on a grand scale. Even earthquakes obey fractal laws. The Gutenberg-Richter relationship shows that small tremors occur far more often than big ones, yet both follow the same statistical pattern. This insight helps seismologists map risk zones and better prepare for the unexpected. Music lovers, listen closely. Certain composers, from Bach to modern avant-garde, embed fractal structures in their melodies. By repeating motifs at different tempos and pitches, they create pieces that feel both familiar and endlessly fresh, proof that mathematics can compose the soundtrack of our lives. Cities grow like living organisms, and their streets often form fractal networks. From the tight grid of Manhattan to the winding alleys of historic towns, road layouts balance efficiency with organic growth, minimizing travel distance while preserving a sense of discovery. Finally, think about the pictures on your phone. Fractal compression algorithms shrink images by storing the self-similar patterns instead of every pixel, delivering crisp visuals with a fraction of the file size. That's why many modern apps can stream high-resolution content without draining your bandwidth. These 10 facts barely scratch the surface of a discipline that bridges art, science, and technology. From coastlines to code, fractals reveal hidden order in chaos, reminding us that the universe loves to repeat itself on every scale. But that's just the beginning. In Part 2, we go deeper into the math, explore how artists harness these patterns, and uncover practical tools you can use right now. Stay tuned, because the journey into the infinite has only just started. Welcome to Part 2 of our deep dive into fractal geometry, where we move beyond the basics and explore the intricate tapestry that weaves mathematics into the very fabric of nature and technology. First, let's travel back to the origins of the field. While Benoit Mandelbrot formalized the term fractal in his groundbreaking 1975 paper, the seeds of the idea sprouted centuries earlier. The 17th century polymath Gottfried Wilhelm Leibniz imagined a world of infinite complexity, a concept later echoed in the work of German mathematician Georg Cantor, whose investigations into set theory laid the groundwork for describing objects that defy traditional dimensions. By the early 20th century, mathematicians began constructing explicit fractal objects. Helga von Koch introduced the snowflake in 1904, a curve that adds ever smaller equilateral bumps, creating an infinite perimeter within a finite area. Wacław Sierpiński followed with his triangle in 1915, a recursive removal of central triangles that yields a structure with zero area but infinite boundary. These early examples illustrated the paradoxical notion that a shape could possess detail at every scale, a property that would later become the hallmark of fractals. Fast forward to the late 1970s, and Mandelbrot's provocative book The Fractal Geometry of Nature challenged the long-standing Euclidean paradigm that dominated scientific thinking. He argued that many natural phenomena, coastlines, clouds, mountain ranges, exhibit statistical self-similarity, meaning that their patterns repeat in a probabilistic sense across scales. To quantify this, Mandelbrot introduced the Hausdorff dimension, a non-integer measure that captures the degree of roughness or fragmentation of an object. Where a line has dimension 1 and a plane has dimension 2, a fractal coastline might possess a dimension of 1.25, reflecting its intricate, jagged structure. This insight revolutionized fields ranging from geology to economics, because it offered a mathematical language for describing phenomena that previously seemed chaotic and unquantifiable. At the heart of fractal generation lies the concept of the iterated function system, or IFS. An IFS consists of a set of contraction mappings, each a simple linear transformation such as scaling, rotation, or translation, that are applied recursively to a shape. Starting from a single point or simple geometric figure, the system repeatedly applies these mappings, producing a limit set that displays self-similarity across infinite iterations. For example, the famous Barnsley fern is generated by 4 affine transformations, each with a specific probability of selection, yielding a leaf that mirrors the elegant spirals of a real fern. The distinction between exact and statistical self-similarity becomes crucial. Exact self-similarity, as seen in the Koch snowflake, repeats identical patterns, whereas statistical self-similarity, evident in natural objects, repeats patterns that are similar but not identical, reflecting the inherent variability of the real world. Insights from contemporary experts have expanded the reach of fractal theory far beyond pure mathematics. James York, a pioneering chaos theorist, highlighted how fractal attractors govern the long-term behavior of dynamical systems, showing that seemingly random motions can settle onto a fractal structure in phase space. In the realm of computer science, Michael Barnsley refined IFS theory into practical image compression algorithms, enabling high-resolution photographs to be stored using a handful of transformation rules, a technique that leverages the redundancy of self-similar patterns. Meanwhile, engineers like Lars Hufnagel are pushing the envelope with fractal antennas, whose repetitive geometry allows them to operate efficiently across multiple frequency bands while occupying a fraction of the space required by conventional designs. Such cross-disciplinary collaborations underscore the versatility of fractal concepts, turning abstract equations into tangible innovations. Why do fractals matter today? Their influence permeates both the digital and physical worlds. In computer graphics, fractal algorithms generate realistic terrains, clouds, and textures by mimicking the statistical self-similarity found in nature, providing designers with tools to create immersive virtual environments. In materials science, fractal patterns guide the development of porous structures that optimize surface area for catalysis or filtration. In medicine, fractal analysis of vascular networks aids in diagnosing pathological conditions such as tumor angiogenesis, where the branching patterns deviate from normal fractal dimensions. Moreover, the financial sector employs fractal models to capture market volatility, recognizing that price movements often follow heavy-tailed distributions characterized by fractal scaling. Even neural networks, the backbone of modern artificial intelligence, borrow from fractal concepts to construct deep architectures that efficiently reuse features across layers. As we explore these applications, it becomes clear that fractals provide a unifying framework to address complexity across scales. By embracing the idea that nature repeats patterns, whether in the branching of a tree, the distribution of galaxies, or the fluctuations of a stock market, we gain predictive power and design flexibility previously unattainable. This synthesis of theory and practice exemplifies the transformative potential of fractal geometry, turning mathematical curiosity into a cornerstone of contemporary science and engineering. In the next segment, we will delve into the practical techniques for visualizing and modeling fractals using modern software tools, empowering you to experiment with these concepts hands-on. Finally, let us consider the philosophical implications. Fractals challenge the notion of a smooth, deterministic universe, suggesting instead a world where irregularity is the rule and hierarchy emerges naturally from simple rules. This perspective resonates with modern understandings of emergence, where complex behavior arises from the interaction of simple components. In this light, fractal geometry does not merely describe patterns, it offers a lens through which we can reinterpret the underlying order of reality itself. As we continue our journey, keep in mind that every leaf, coastline, and data set you encounter may conceal a hidden fractal skeleton, waiting to be uncovered. In Part 3, we uncover what mainstream sources won't tell you. Imagine looking at a simple fern leaf and feeling the pull of a secret that spans the cosmos. It starts with a whisper, a faint hum felt by those who study the edges of mathematics, where lines bend and repeat like an echo in a canyon. In the first revelation, we meet the forbidden formula, a set of numbers that dances beyond Euclid's straight-line world, coaxing branches to sprout in perfect self-similarity. This hidden equation is the silent conductor of lightning bolts, the silent architect of the spiraling arms of distant galaxies. As we journey deeper, we stumble upon a lost dimension, a realm where scale becomes irrelevant and every detail mirrors the whole. Picture a coastline, from satellite view down to a grain of sand, the jagged edge repeats, each crest a miniature replica of its larger counterpart. This is not coincidence, it is the universe's way of conserving complexity, a principle that explains why clouds form the same fluffy clusters whether you watch them from an airplane or from a mountaintop. The secret code that follows is more than an abstract curiosity, it is a universal algorithm encoded in the very DNA of nature. Scientists have translated the growth pattern of a nautilus shell into binary, uncovering a sequence that predicts not only biological development but also the rise and fall of stock markets, hinting at a deep, mathematical resonance between life and economics. Then comes the unexpected bridge, a startling connection between human-made structures and celestial formations. Architects now embed fractal motifs into skyscrapers, creating facades that flex with wind like a tree in a storm, while astronomers map the same patterns onto nebulae, finding that the turbulence of interstellar gas follows the same recursive rules as concrete beams. This bridge shows us that the same mathematics that keeps a building standing also guides the formation of star clusters, erasing the line between art, engineering, and astronomy. Finally, the revelation arrives: fractal geometry is the hidden syntax of reality, a language spoken by every level of existence. From the microscopic helix of DNA to the sprawling web of galaxy clusters, the pattern repeats, each scale echoing the next. Understanding this pattern is not just academic, it reshapes how we design technology, predict natural phenomena, and even perceive consciousness itself. The mystery that began as a simple question, what secret patterns hide in everyday shapes, unfolds into a tapestry of connections that bind the smallest particle to the largest cosmic structure. Each chapter of this story builds on the last, pulling you deeper into a world where the ordinary becomes extraordinary, where the familiar reveals hidden depths, and where every revelation cracks open a new layer of wonder. Stay with us as we untangle the threads, because the next part will flip your perception upside down. Now that you know the truth, Part 4 will change how you see this forever. Welcome to Part 4 of our deep dive series on fractal geometry. In the opening chapters we trace the intellectual lineage from Cantor's paradoxes to Mandelbrot's revolutionary vision, establishing the historical scaffolding that supports modern research. We then unpack the core mechanisms, self-similarity, fractional dimensions, and iterative function systems, showing how simple recursive rules generate infinite detail. Moving from theory to nature, we examine trees, lungs, river basins, and coastlines, quantifying each with Hausdorff dimensions that reveal hidden order in apparent chaos. Turning to mathematics, we explored the Mandelbrot set and its escape-time algorithm, demonstrating how computational power transforms abstract equations into vivid visualizations, while wavelet and multifractal techniques extend analysis into turbulence and finance. The field is not without controversy. Critics caution against overextending the fractal label, sparking vigorous debate about its relevance to quantum physics and stochastic modeling. Yet these disputes sharpen the discipline, prompting clearer definitions and more robust applications. Looking ahead, we see fractals infiltrating AI-driven image compression, medical diagnostics, and bio-inspired architecture, proving that the geometry of complexity is a practical tool for innovation. By mastering these concepts, you gain not only theoretical insight but also a versatile lens for solving real-world problems. If this series gave you value, subscribe. More deep dives coming every week.